drawing standards. Why? Here's why. This is the typical kind of sketch you might get if we didn't have any British standard drawings, any ISO standard, international standard, American standards. This is, if you like, a technical sketch. If you're not sure what it is, well, you probably haven't made one yet, but there's a drill drift. In the bad handwriting you can see it's 170 long. Although we don't know 170 what. We can see looks like a hole there, and well, I can barely make out what size that is. It's got a 7mm countersink. Looks like it might be a 5. This we can see is 130 long. This I think is 6 long. Make radius 3mm. There's a dimension here, so from the hole to here is 20mm, and it's 20mm from there. There's information on there, but would you be able to make it? Would you be able to make what you think was the right thing? But you probably would never get to producing the 100 off that's being asked for and having them all come out the same, particularly if you have more than one person doing it. Look at some of the problems. This is 130 long, but is that measured on the angle, or is it actually measured in line with here? Because anyone with the first idea about maths will tell you that one length is going to be longer than the other. The hypotenuse is always going to be a little bit longer. And that seems to be drawn on the hypotenuse. This 20mm, well, we know it goes to that point, but where? To the edge of this 7mm countersink? To the edge of the hole, which looks like it's 5mm? Or to the middle of the hole? We don't know because it's not standardized. We could make one of these. We could make an approximation of what the person that asked for it wanted, and there's a goodish chance we'll get it nearly right enough to be usable. But to get 100 of them made repetitively, identically, by a team of say 20 people, it ain't happening. We need to standardize. So that's what we're going to look at. So this is how it should look. We've got some common dimensions that you saw in that hideous sketch. It's 170 long. We've got that 130. But look, we now know how it's laid out. We know how it's measured. We know that this dimension here, this 150 for this length, is taken from the centre because it shows it on the drawing. So these are parts of the standard that go into making drawings understandable by everybody. That's why it's so important. We get an understanding of what these things mean. The layout of a very simple tool like this is fairly easy to draw up, fairly easy to understand, but there's important bits that we need to get a handle on. One of the most critical, one of the ones that we see on nearly every drawing that we ever have to work on, is where there's a hole. Now, holes are routinely measured by diameter, and critically with diameter we use a specific symbol, and here we have the symbol. So it's a circle with a line going through it. You can kind of imagine, I suppose, if you need something to jog your memory, that it's a hole that somebody's laid a rule across to measure it. So that symbol there is known internationally as meaning diameter. It's one of the key British standard, ISO, ANSI, you name it, symbols that tell everybody who's working on any kind of engineering drawing that we are talking about a hole with a diameter of, in this instance, 5mm. By the way, we know it's millimeters because if we look down at the bottom of the drawing, dimensions in millimeters. If we don't put that on, we're going to need to put the actual dimension indicator next to the numbers on our drawing. But by putting that on, which is a standardized format, we can ensure that the operator who is looking at the drawing will have a good understanding that all the dimensions are in millimeters. So there is no guesswork. If you're in one of those sticky situations where you have to say dimensions in millimeters and some are in inches, and we get that, We work for Ford, they're an American company, so we do have a mix and match of measurements. The drawing should say dimensions in millimeters unless otherwise stated. So that key symbol, one of the first ones you need to learn, is for diameter. Also along from here we have one of the standardized abbreviations that we see used in drawing again throughout the world. C''SK, countersink, and then there's information afterwards. So it's countersink to a diameter of 7mm, and it's a 90-degree countersink. You can just see another standardized symbol, it's pretty small here, but the little degree symbol up next to the 90. Both tells us it's done on both sides. So that single line of information that we have running across there on what is called a leader, so this line coming up here with the arrow points to where the information is relevant. That single line of information tells us everything we need to know to drill and countersink that hole in that component. It's a really critical part of the whole standardization of drawing. So plenty of other information on the drawing. Down the bottom here we've got the title blocks. Quickly starting over here we've got the description of what the actual item you're producing is. Much easier in communication to say I've got the drawing for the drill drift, I need to know. Next along here we've got the material, in this instance bright mild steel. So when you're looking at an individual component made out of one piece of material, that will be specified on there. More complicated assembly components, that won't necessarily be listed, but in the individual breakdown of the component, the material will always be mentioned. We've got, as we previously looked at, the dimensioning block here, so we know what dimensions the actual product is produced in. Critical to know. Then we have a piece of information which tells you the type of drawing that you're actually looking at. In this instance, third angle projection. Here's the British Standard symbol, which doesn't necessarily help to explain what it looks like, but it shows you at a quick glance, once you're familiar with it, that it's either a first or a third angle. Finally, at the bottom we've got the general tolerancing, in this instance plus or minus 0.4. So here it can be 20 ideally, then it's perfect. It can be 20.4 millimeters, or it can be 19.6 millimeters, and it will still be a usable product. At the end here we've got the scale, we've got who actually did the original drawing, and we've got the date that the drawing was produced. Sometimes you'll have version numbers on there. These are very simple drawings, we don't have that kind of thing on here, but more information can be added. Scale is an interesting one. It says it's 1:1. Let's have a look. Well, we've got the drawing here. That's produced from my printer. Put those two up there. Put those two, and that's not far off. It's pretty much the same size. It's not exactly right. There's an important consideration on this. When we print a document, we send it through a standard, either business style or even home style printer, and that printer produces the printing by vaporizing small quantities of ink and blasting them onto the page. They're never what we call mathematically correct. The truth is, this dimension from here to here, although it says 170, it should be at a 1:1 scale 170 millimeters. It won't be. There will be errors. The thickness in the lines will be wrong. It'll be blurry even though we can't see it. They're not accurate enough for you to actually be able to take a rule or a vernier, take a measurement of something and then transcribe it across. Only go by the written annotated dimensions that you have on the drawing. Don't take a measurement directly from the drawing, because it won't be accurate enough, particularly when it's printed. Final bit of British Standard that we've got on here. Most of you used it in your Q&A. It's the surface finish symbol that we've got here. Kind of this tick, or looks a bit like the square root symbol that you might know from maths. Can also come without this top line here, and that just represents the surface finish of the particular item that you're producing. In this case 1.6 microns, which we would check by using a scratch block which would allow us to, by feeling how 1.6 microns feels under our finger and comparing it to our finished product, we'll be able to roughly determine whether we're fairly close to that surface finish. These also come in other variants, so you can get where the 1.6 is here, you might see a circle which has been drawn on there, or a line that goes across. So the circle means you're not allowed to remove any material to produce that surface finish. It must be cast or forged or supplied to you with that surface finish before you start manufacturing the finished product. There are lots of variations in it, far more in depth than we need to go in at our level, but the surface finish symbol that we see here is one that you can always use time and time again to talk about British standards when we're looking at those questions on our Q&A. Okay, let's look at datums. So we're always being asked about datums on our Q&A. Establishing a datum is one of the most important parts of making a start on producing a product from a drawing. And we tend to think it in terms of what we're going to do with the piece of material. So yeah, we might say we've got a nice straight edge here. It's been machined or rolled and been supplied to us and it's dead flat. I've checked it on the surface plate. So that's going to form one of our datums. And then we might start filing perhaps over on this edge here to get this perfectly square to that edge and say, right, we've established a datum, we're good to go. It's not as simple as that. One of the most important things when it comes to establishing a data is not what you do with the material, it's what this tells you. So if you look at this drawing, it gives us closest to where the datum is. And the datum is always going to be that point on the drawing that the majority, if not all, of the dimensions are taken from. So a quick glance at this drill drift drawing shows us that there are two dimensions here, 150 and 130, taken from this point. Two dimensions here, 6mm and 170, taken from this point. One dimension here, 20mm, taken from this point. This point here is our datum. It will allow us to establish all of the dimensions that we have in this whole product, with the exception maybe of the radius from this point. And it's interesting because it's not even part of the finished component. So in order to establish a datum for this product, we would need to get this bit nice and straight, and we'd need to get this bit nice and square to it, and then use this corner here, once we've established it as a nice accurate datum, to develop all of our different dimensions, up, down, left, right, from that one point. The fact that it will be removed later doesn't matter. This is our datum, this is where we need to start all of our scribing so that we can produce the finished product. We nice to think that datums were all that simple. So here we've swapped over subjects. Now we're now looking at sheet metal. Those of you who've done this will recognise this as being one of the ends of the sheet metal toolbox, and it's a busy drawing. There's lots of dimensions going on here, and so when you're faced with producing this, the first thing you have to ask yourself is, where is my datum point? Convention says we start looking at all of these, so we might look in one of these corners like we've got here and go, okay, we've got a measurement here coming off that corner, we've got a measurement here coming off that corner. But this one doesn't actually. If you look, this is a cumulative dimension, so it starts 6mm from that corner, but then the 8mm starts from the end of that 6mm line. So this 8mm isn't formed from this datum. Same on the other side. Cumulative, don't help. Where's the datums? Well, actually the datum is slap bang in the middle of it, and if you've done enough research into BS 8888, the ISO standards, etc., you may be familiar with this symbol. This isn't just an abbreviation, it's a specific symbol. So we have a C crossing over an L, and what that specifies is what we have here is a centre line, and it's unfortunately been obscured by a lot of this other writing that we've laid over the top to help you follow the folding technique, but nevertheless you can see there's kind of a dotted and dashed line running through here, running up through here, underneath the big arrow and up to the top, and that is slap bang in the middle of what is a symmetrical component. If we folded that in half, the two edges would line up. So that centre line is a key to how we actually produce a datum for this product. So if we look at the top here, we'll see we've got a centre line, and we'll see this top tab here measures a total of 116 millimeters. What that tells us is that to scribe these particular lines here, we have to first establish the centre line by scribing it on our material, and then we will measure 58 millimeters from the centre line to this point, 58 millimeters from the centre line to this point, and that will give us an overall total of 116 millimeters, which will be symmetrical about the centre line. We can do the same at the bottom with the 212 measurement that we've got, and now what we've got is we've established this point and this point and the two outer points, which will allow us to then start building in the 6mm from that edge and the 8mm from that edge. 6mm, 8mm, 5mm, 5mm, and we've got all of those bits marked up in one direction. We've got this established, and we know that from here to the very bottom of this tab is 162. So once we've established this, we can then establish that one, and once we've got the top and bottom lines put in, then we can start to do the rest of the dividing up that is required to produce our finished product. And it all revolves around the centre line. Most drawings the centre line would be a little bit clearer, but that symbol there is a critical one to look out for, because that's telling us exactly what we need to know. With the datum on here, there's the datum, slap bang in the middle. That's where I need to be looking, that's where I need to establish first, and then I can start to develop my finished product until at the end I come out with something which looks a little like this. So we've swapped over now from what was a pattern development drawing to an isometric drawing, which gives us a kind of 3D image of what we're going to be producing. These aren't very good for a lot of dimensions, because the changes in the angles to produce the drawing make it a little bit messy. So we've put most of our dimension lines on the layout drawing. Keep it nice and simple, put them all there nice and flat so you can lay them out. This tells us, however, how we're going to fold it up. We can derive from it the directions in which all of the angles are folded. We can derive some of the spacing, some of the clearances. And it just gives us that understanding. There's a couple of other interesting BS 8888 symbols on here that you can also relate to, and that's these lines here. We've got a line AA and a line BB, and they've both got little arrows pointing from the ends of the lines. These are what we call section lines. So what this is doing here, what AA is doing, is it's saying we're taking an imaginary knife and we're going to chop through the material there along that line, and then we're going to look at that material from this direction, the direction that the arrows are pointing at. And what that will give us is what we see here. This is the cross section if we looked through AA in that direction, and you can see that the metal has been bent round on itself and has come back and is touching, because these top ones are safe edges. On the other hand, BB, if we look at it a bit closer in, BB, if we look at it, we can see we've got a cross section across here looking downwards, and what we're actually going to see is a self-securing joint, not a safe edge. So here we've got the metal curved back on itself, but with a 1mm gap in between to allow us to get another piece of material in to form that nice tight joint that holds the whole toolbox together. So they are really, really useful conventions that we use in drawing that really give you an insight into exactly what the finished product is going to look like when you've manufactured it. To produce a drawing, we need them to not be overflowing with information. This is quite a busy drawing. There's lots of dimensions on it, but when you start doing it, you're going to find that there are some dimensions which are missing. You have to put yourself in the position of the CAD drawer, designer who produced this in the first place. They will assume that you have a limited understanding of engineering, and they will encourage you to make some assumptions based on basic knowledge. So for example, we often get in the workshop asked what the dimensions are regarding these areas here. because there's no width dimensions, there's no angular dimensions. We've got a little bit of dimension here, but nothing more. Well, the reality is all the information that we need is on here. We know, for example, that all of these dimensions along here are square to these dimensions that we've got here, so they're perpendicular, which means that if we draw a line from here to here, this is going to be 90 degrees. If we look here, we've got two cuts made, and they, by the fact that these two lines here are parallel, we know that they are equal angles. So if we cut 90 degrees into two equal portions, we don't need to be a maths genius to work out that these are 45 degrees each, which makes that actually relatively simple to draw in. In terms of the dimensions, if we look to the next drawing, we can see that these three top pieces all line up and are exactly the same. So they all line up perfectly along the top here. So that tells us that this dimension from here to here must be the same as the dimension from here to here, and the same as the dimension from here to here. So therefore, whatever this dimension is, in this case 14 millimeters, will be the same from here to here, and this top one from here to here will be the same as this one here, which is 6 millimeters, which is actually reinforced over on this side. So we now know that this line here will be 14 millimeters from this one, and this line 6 millimeters from that one, and we know that they're at 45 degrees to this angle, or this angle that we've got here. Actually, the information is there. It's not been hidden to make your life harder, it's actually been removed from the document to make life a little bit easier for you. Information overload on these things can be really problematic and make life very difficult for you when you're trying to mark things up. So putting critical dimensions on there that we must know, we must get right, and then allowing the intelligence of the manufacturer to make some basic assumptions based on our understanding of BS 888, ISO standards, etc., will allow us to leave some sections out and still finish up with a correct product. And here's a toolbox hinge. Some of you will be familiar with this, which again shows the cross section, and actually you can really see how useful the cross section is. Although this drawing shows us a rough indication of how the finished product is going to look, and it gives us some useful information on some of the drilled hole spacing, etc., that we didn't have on the other drawing, it doesn't actually show us what the cross section of the hinge is going to look like. Without this particular line here giving us this sectional drawing that we've got up the top here, we wouldn't really understand how that curved part forms, how we have a self-securing joint here with a 1mm gap, and how it then goes down and folds out to make the lip for the shelf that goes into the top of the toolbox. That's a critical point, that section AA. Without it, we would have no idea how this whole process goes together to produce the hinges. We've also got some slightly more unusual marking out here, which is these holes that we have here. So we've got a leader here, it comes up and it tells us it's a diameter of 3.3 millimeters, and that the holes will be drilled in 3 places for aluminium pot rivets. You'll notice that there's no dimension to tell us where this goes. However, if we go down to the other end here, we can see that it is spaced at 30mm. And so, by convention, we therefore assume that this one, as they've not told us otherwise, is also spaced at 30mm. This one here has no dimension at all, but again, by convention, the assumption can be fairly made that this will go in the centre of the hinge unit that you've produced. Nice easy drawing, this one. Couple of points to make out. Very few dimensions on here. First thing to look for when you're looking at a drawing is there any written information that we need to know, and there's 2 useful boxes on here that we need to pay attention to. First one at the top is this notes. There is a specific hand bender used for this item, so there is a machine which has been developed to produce that. So that probably tells you that you don't need to worry too much about these dimensions that we've got here at this point, certainly until after it's come out of the machine which actually produces it. Second important piece of information is here, developed length. What that tells you is how long this piece of bar needs to be before we start bending it. So you get the whole piece of bar from the stores and you need to cut 435 millimeters of that bar off for you to then make this finished product. The material, as we can see, is a diameter 6 millimeter mild steel, which tells us it's a mild steel bar. And then we know we can put it in the special machine that you'll be shown how to use. It has a leader here that says R5 4 places. So if you remember when we spoke about radius before, R5 specifies that it is a 5 millimeter radius. So that's exactly what these should measure in here. And the machine is actually set up to produce those for you. So you can't really change those. There's also dimensions in here. And the dimensions are there for checking only. If you use the machine accurately, this is exactly what you should get. You should have 100 mil on the inside. Notice that these are on the inside, not the outside. And you should have 120 mil across the inside at the top. If they are all correct, then your finished item should be exactly right. There's tons of information available online. Some of these reference books are really useful. The Zeus book has some really good information on drawing. I think the Pocket reference book, which we have some available at CME, and if you ask Keith, he can actually arrange and get one for you, I believe, has some really useful information in there. Here's some of the standards. This is a useful comparison because it gives a difference between the ANSI, which is the American standards, and the International Standards Organizations, the ISO. And you can see that there are some crossovers, angularity, but then you can see there's some other things which they have a completely different symbol for. All-round profile, for example, here you see there is an ANSI symbol. There's nothing in ISO. So one of these cross-reference books could be useful, particularly for you guys where you're going to, throughout your careers, be dealing with stuff which is manufactured in America as well as stuff manufactured in Europe. So it's useful to be able to cross-reference some of these commonly used symbols. And again, these are just some of the basic commonly used ones, and you see there's plenty of them. Also in here we have some common abbreviations, and these are quite relevant to some of the stuff that you've done already for your Q&A. Notice the center line there. There's two options, CL or the actual CL, which is crossed over there. So that's quite a common one that we've already just discussed. As you can see, there's loads of them, and this is just a small portion of them, the most commonly used abbreviations that you'll find in engineering drawing. It looks initially, when you look at it, as being a little bit of a foreign language. It is done with common sense, and it's done with a very positive outcome in mind. Start to gradually get used to what you see on the drawings. And again, the most important thing with any of this stuff when you're looking at a drawing or any piece of information for a task that you've been asked to do, if you're not sure, you need to ask somebody. You need to get hold of whomever's taking the lesson with you and just inquire what that symbol means. That way you won't make mistakes that are going to end up meaning you possibly have to redo the whole project from the start.